One is about arc length and sector area. And it seems unrelated because we talked about angles a bunch and now we're talking about lengths and areas. But they're very related to radians, and it's a huge portion of why radians are useful, because it lets us measure things on circles. It's easy to measure things that are straight. Right? If you have straight lines, you can take a ruler, you can measure it. You can take whatever measuring device you have and measure that out. But like I said early on, like trigonometry was invented because they were trying to measure curved surfaces. They were trying to look at distances on Earth that they knew was round. They were trying to measure distances out to the sky where you have all this stuff that's like not actually a straight line. And so they had to come up with ways to measure those distances out. And so we had to figure out, well, if we have a circle and I have 2 points on a circle, how do I know how far apart those 2 points are on the circle? Right, so think about like if this was Earth and you have like this is San Jose, and let's say like Tokyo is, well, it's like on that side somewhere. Right, so we have to go around. Well, this is a curved surface, so we want to know the distance, but it's not a straight line from San Jose to Tokyo. It's a curved line because we have to follow around the curve of the Earth. That distance is called the arc length. That curved line that we draw, that's called an arc, and so the length of the arc is the arc length. We can also measure things like area. This is probably easier to think about in a pizza, probably. Or like a cake or a pie, like anything that's round that you cut up. So let's think about a pizza. Right, if I have a pizza that's more perfectly round than what I drew, we can cut it up into slices. Right. So imagine this was a 18-inch pizza that you bought. Right, so we know that the diameter of this is 18 inches. That means this is 9 inches, 9 inches, 9 inches, and 9 inches. So now I want to know how, if you just take one slice from these 4 slices, it's a pretty big slice if that's an 18-inch pizza. What is the length of that crust on the pizza? That's the arc length. And then how much pizza do you have? Right, the area of that like curved triangle piece. It's not a proper triangle because it has a curved side on it, right? It's not a straight line on that side. That's called the sector area. When you cut up circles into pieces, those pieces are called sectors. So we want the area of that portion, and we want the length of the outside bit. Both of these things depend on angles. Because if you think about it, if I'm cutting up my pizza, I can cut it. When I'm cutting it up into angles, right? I'm making 90-degree angles here, or pi over 2 radian angles there. If I cut it up more, then I'm making those angles even smaller. So if I make an 8-slice pizza, now I have these 45-degree pieces. And those angles are what determines these lengths, because those are just kind of like magnified versions of them. And so the arc length and the sector area depend on the angle. Now the angle measure we have that depends on the circle back, right? So this interdependence is radians. So we need to use radians for this. But all we have to do is use a fairly simple formula for it. For arc length, we get a formula that's basically, it's a, what's the word I'm looking for? It's a proportion of the based on the angle and the radius. So arc length is usually specified as S. S is arc length. And that equals the radius R times theta times the angle. So it's just taking that angle and multiplying it by whatever radius your pizza or your circle has. So S is the arc length, R is the radius, and theta is the angle, but this angle has to be in radians for this to work out. because radians are the units that convert between overall circles to angles. Degrees don't do that, so we have to use radians for this. Sector area is very similar. To find sector area, it's also a scaling kind of like that. For sector area, that's going to be r squared times the angle divided by 2. Here, area is the sector area, so A is sector area, R is radius, and theta is still angle in radians. This is how the two main formulas you know for circles come out. Arc length is just a portion of the circumference. So if I think about, let me do this on a different page. So I know my whole circle has a circumference. That's the length of going all the way around the circle. Right? So if I wanted to go all the way around, the length of that is the circumference. That is also the arc length of going all the way around. So my theta of going all the way around is 2 pi radians. So the circumference following the arc length formula would be r theta. That's r times 2 pi. And you get this formula for circumference, 2 pi r. That's the formula for circumference you learned in geometry. Same thing for sector area. If I wanted the area of this whole circle, then the area would be r squared theta divided by 2. Well, theta is 2 pi, and dividing it by 2, so the 2's cancel, and you get pi r squared. That's the formula for the area of a circle. So sector area and arc length are very similar to the circumference and area. In fact, they are the circumference and area of the circle, and we're just cutting it down based on the angle. So if we don't want the whole circle, we just want that bit of the circle, then we just need to remove this whole angle, change the angle to whatever that piece is, and we'll get the new length on the outside and the new area on the inside. So let's actually try doing a practice problem with this. So again, words are kind of long in this. It says, what is the length of an arc subtended by an angle of 30 degrees in a circle with radius 5 centimeters? So let's think about this a little bit. So we have a circle, and all this like subtended by an angle, it just means that like when we're cutting up the circle, we're using an angle of 30 degrees. So if I go from the center out to the end, that's the radius. I know that's 5 centimeters. And if I go 30 degrees, well, that means I go up a little bit, but not too much. Right? That's a 30-degree angle. So I want to know in this piece, what is the arc length that's created? What is the length of just this piece of it? So my arc length formula is r times theta. I know that r is 5 centimeters. And I know that theta is 30 degrees. But remember, it said that theta has to be in radians. So we have to take 30 degrees and convert it to radians. So I multiply it, put degrees on the bottom, pi on the top. That way I get radians in the end. The degrees cancel, and I can reduce this fraction down. I'll get pi over 6. So now I can just substitute that into my formula. R is 5 centimeters times the angle pi over 6. And I get the arc length is 5 pi over 6 centimeters. And I can calculate that, 5 pi over 6. That's about 2.6 centimeters. So I know that that piece of the circle is 2.6 centimeters long. So one more problem. This is a word problem, similar setup. So we have a softball field, but it's only given us this bit of the field, right? So it doesn't have to be a whole circle. As long as you can see that it's part of a circle, we can still use these formulas, as long as it's just something that's curved. So we have this bit that's curved, and we know it makes a 90-degree angle over here. So we know that the theta is 90 degrees. And we know that these bits are 200 feet, which means the radius is 200 feet. We want to find the length of the fence over here, which would be the arc length. And we want to find the area of the field, that would be sector area. So length of the fence, which is the arc length. So that would be taking our formula for arc length, which is r times theta. Well, theta has to be in radians again, so I'm going to multiply this to get rid of the degrees. Remember again, if you get nothing else out of this week, knowing how to convert between degrees and radians, that's like the most important thing. Because see how it keeps coming back in these problems. So r is 200 feet, and theta is pi over 2. Remember I said that radians don't have units, that's why we're not writing any units here. We just know that they're radians, but they don't have a unit attached to them. They just take on whatever length measurement we have. So the 2's will cancel, right? So 2 goes into 200 100 times. You get 100 pi feet, which if I calculate that, so 100 times pi is about 314.2 feet. So that's the length of this fence. This is 314.2 feet. Next thing we want to know is the area of this whole piece. So the area of the field, which is sector area, that uses the formula r squared times theta divided by 2. So I take my radius, 200 feet squared, times the angle, pi over 2, and divide that by 2. So I can start simplifying this down. 200 squared is going to be 40,000. Pi times pi over 2 over 2. And this is feet squared. The 2 can go into 40,000 and make that 20,000. And then this 2 can go into it again and make it 10,000. So we get 10,000 pi feet squared. And if we want to estimate that, that's about 31,415.9 feet squared. So that's saying the area of this whole field is 31,415.9 feet squared. So these styles of measurements and calculations end up being a lot more useful to us than the areas of squares and rectangles, because a lot more things in the world have some curved surfaces on them rather than just all being straight edges. And that's where this gets used a lot, and kind of why this is more useful to us, especially in the sense of thinking about astronomy and looking at stars and stuff, but also just generally mapping out the world and measuring distances and creating maps and navigation and planes and ships and GPS all kind of works this way.